Welcome to a quick tutorial about pasta, sort of. It's a Grasshopper tutorial, and we're going to explore surfaces and meshes by making pasta. We'll learn a little about how math equations can be used to create surfaces. Surfaces in Rhino and Grasshopper have u and v coordinates you're probably familiar with. Surfaces are two-dimensional, meaning we only need two coordinates to navigate to any point on the surface. So we'll be looking at how those two-dimensional u, v coordinates get turned into three-dimensional x, y, z coordinates. And then we'll treat the u and v inputs as discrete inputs rather than the continuous nature that the surface class provides, so that we can move from a continuous surface into the territory of meshes, discrete meshes. We can think of a mesh as a discrete version of a surface, just like a polyline is a discrete version of a curve. And computers really do prefer discrete over continuous. This is how they operate, in discrete steps. So we'll use math equations and discrete u-v values to make a mesh in Grasshopper. And this really is surprisingly easy, especially since we won't be making the math equations at all. We'll be using equations from the world's nerdiest cookbook. It's not actually a cookbook, but it does deserve an award. The book's called Pasta by Design by George L. Legendre. We're going to pick just one page from this book. I didn't want to give too much away from the book. There are a lot of twists and turns and I don't want to get sued, so I just had to pick one pasta. The one on the cover, farfalle, it looks great. And it means butterfly in Italian, which brings in nature. But that's not a very interesting way to connect to nature at all. And there are way too many layers to this equation. It would take forever to go through, and that would make this not a very quick tutorial. Also, by the way, I'm sure George Legendre is a great guy. I bet he wouldn't sue. And for real, if you have the means and you can find this book, definitely buy it. Delightful really is the best adjective I have for it. Put it on your coffee table, browse through it, it's very cool. So anyway, I was stuck between cavatappi and fusilli as the simple representatives to show how math equations can be used to construct surfaces. How surface points can be made into meshes. Both pastas are good with creamy sauces. Both have helix qualities. Both have simple equations. Fusilli reminds me of a little too fancy rainwater capture system. And cavatappi reminds me of a coiled plant, like cucumber tendrils. It doesn't really matter, it's the process that's important though, using these equations to make surfaces. And cavatappi has an extra layer of texture, so I just went with that. So instead of nature guiding the math or guiding the design, it's pasta. A little more delicious than the usual Nuluka topic. Quick though, short and sweet, let's just get into it. I'm going to start by getting a panel. And I'll type 70, enter, and then I'm going to right click and go to multi-line data so we can get multiple entries in here. Let's do 70 and then hit return and then 150. These are going to be the number of u and v increments we have. In the book, Legendre calls these ranges, and he calls u and v I and j. We're just doing u and v so we can connect it to the Rhino u and v on surfaces. So eventually this is just going to give us two lists of integers, 0, 1, all the way up to 70, and 0, 1, all the way up to 150. We're going to plug these in to three different equations to get our x, y, and z coordinates. We're going to plug all of the integers in. We're going to plug 0 for u and 0 for v in, then 0 for u and 1 for v in, and 0 for u, 2 for v in, and so on. We'll just keep plugging in different combinations until we have all different combinations of 0 through 70 and 0 through 150. So instead of trying to explain that right here, I should just move on. I'm going to get another panel though and write u, multi-line data, and enter v. Now we have u and v just so we remember what these are for. So let's make those two lists, 0 through 70 and 0 through 150. I'm going to get an integer component and call this uv because we're going to combine this into a little component to save space on our canvas eventually. First thing I'm going to do is just get an addition and add 1. And this is because we're not actually going to have 70 integers in the first list and 150 in the second. We're going to have 71 and 151 because we're including 0 in this list. And then we'll get a series component, 2 of them actually, and we'll dispatch these 1 into each series component as our counts. So now we have a list from 0 to 150 in that one, and a list from 0 to 70 in that one. The next thing we want to do is cross-reference. We want to cross-reference all of these values. So let's get a panel to see what's coming out here. So for A, we have 0, and it's hard to tell here. Let's plug in B. All of these are 0, and we're going to go 0 70 times until we get to 70, and then we'll go up to 1 70 times. This is basically just making it so that if we've got every combination of U and V in these A and B outputs, so there are 10,721 coming out of A and B. So this is how we're going to get 0, 0, 0, 1, 0, 2, all the way up to 0, 150, and then we're going to go 1, 0, 1, 1, 1, 2, all the way up to 1, 150, and so on. We need all the combinations of U and V. So I'll delete that, and we can get two more integer components, a U and a V. And let's get two output components, because we're going to put this into a cluster. Before I cluster it up, there are some other things I'd like to bring out of this that we'll need later. We won't need it right away, but we may as well just, since we're going to put this into a cluster, we may as well just make them now. I'm going to get another dispatch component, and before we add one, I'm going to get two more integers. These are just going to be our U max and our V max. This is the last number in each list. So coming out of this is 70, and coming out of this is 150. Let's get two more outputs. We'll need these later as we change our equation. So don't worry about this now. But there is one more thing we can get that will be helpful later. Another integer, and we can call it partition. I think that's how you spell partition. Yes. Okay. So partition we can just bring out of this A up here, and it's just going to be 71. What we're going to use for this later is to separate all of our points into different branches, and in each branch we're going to want 71 different points, because there are 71 different values along the first line of U values. So we have 71 U's along, you can imagine it like a row, like a matrix or whatever, a grid, 71, and then there's another row of 71, and another row of 71, and another row of 71. And there are in total 150 different rows of 71. And we need that number when we're going to use it for the partition list component a little later on. So let's get another output. This will be our last output for this. And let's package this into its own little component. And let's call it get UV. Okay, next we can just write our equations. This is, and again, these equations are coming right from Pasta by Design, the book, page 39. And each equation is going to take in a U value, a V value, and it's going to output one coordinate value. And so we'll have three different equations. One will output all of the X coordinates, one will output all of the Y coordinates, and the last one will output all of the Z coordinates. So let's write these equations. Let's get a panel, and in it write parentheses 3 plus 2 times cosine, open and close parentheses. Inside this cosine we're going to say U times pi divided by 35, and I just wrote pi for pi. The evaluate function component will understand that as pi. Then plus 0.1 times cosine, open and close parentheses, and then inside these parentheses we say 2 times U times pi divided by 7, and then we're going to close the first parentheses that we made. Then times cosine, open and close parentheses, V times pi divided by 30. And that's it. This looks right. I'm going to get a evaluate function component and plug it in to make sure that it's working. I'll type in evaluate, this f of x, and instead of x and y we need u and v. We can plug in our u and v values from here. I'm going to hide these inputs. and that's our function. So now we have 10,721 outputs. These are going to be all the x coordinates for our points. So we can call this x. And for our purposes, it doesn't matter which one's x, which one's y, and which one's z. We just need one of each. It'll just change the way the pasta is oriented. So I'm going to copy this. Let's call this one y. And the only thing we need to change in this equation is this last cosine. Let's write sine instead. Then let's copy it again. Let's write z. And then inside, there's a couple changes we're going to make to this. First, I'm going to get rid of this parentheses and this one. We don't need them anymore. So I just got rid of the first one and the one after 2u pi divided by 7. Then let's change this first cosine to sine and the second cosine to sine. And instead of times sine all of this, we'll do plus v divided by 6. Okay. And I should zoom into perspective for the dramatic effect. Let's plug these into construct point component since we have all of our x, y, and z coordinates. Okay, and so now you can see what the pasta looks like. We don't need this grid anymore. So these are just points. Our next step is to turn all of these points into a mesh. That's where the partition list component comes in. This is our list, and these are our partitions. So I'm going to get an integer component. I'll copy partition, and we'll rename this component. Plug it in here. Wire display hidden. Let's bring that down here. So now what we have coming out, I'm going to simplify this so it's easier to read. We have 151 branches, 0 through 150, and each branch has 71 items in it. All of these items are points. So now that we have these in a tree, the reason I did this is because I already have a component that will take a tree, a data tree of points, and turn it into a mesh. This is another tutorial by New Luca. It's a very quick one that's just writing a C# component to do this exact thing, make a quad mesh. A mesh where all the faces have 4 vertices out of a data tree of points. So we can rewrite that real quickly here in case you didn't watch that tutorial. So I'm going to get a C# component. We only need one input, and this can be called input points. And it's going to be tree axis, so right click and go down to tree axis. And we need to go to type hint. So if you aren't familiar with scripting inside Grasshopper, or if you don't know much about C#, you always need to tell these components what kind of data is coming into the inputs, or you usually do. In our case, it's points, so we go to type hint point3d. And then once we're inside, this is the part of the script that's going to run every time this component runs, which is every time the input for this component changes, or every time the canvas is recalculated. That's this first little white blank spot here. And then down here, we can create our own functions. They call this just custom additional code. This is whatever else, if you want to create a class or create a function to use up here, then you just write it down here. So if this feels like more effort than it's worth, following along as we write this C# component, then feel free to download this script from the Pavilion website. I'll link to that. Alternatively, you can just copy the code and paste it into your own scripting component. And feel free to visit the Pavilion website whenever. New videos are always here first, and there are videos here that will never be on YouTube. So back in our scripting component, if you're pretty new to C#, I apologize. I'll be going pretty quickly through this part, but I will try to explain a little bit step by step why I'm doing what I'm doing. And so maybe this can still be helpful for you. So first, we're going to make a function that returns a mesh. And we have to, when we're making a new function, we need to explicitly say what that function is going to return. It doesn't always have to return something. We could write void, but in our case, we want a mesh coming back. We want this function to create a mesh, and then we can call it whatever we want. We'll just say create mesh from tree. And then next, we're going to have an open and close parentheses. This is where we put our inputs for the function. The inputs are going to be data tree point 3D. That's just telling the computer what kind of data is coming in, and then we need to give it a name, and we're just going to call it input tree. Or we can call it input tree, that's fine, but since we called it input points up here, we may as well just call it input points down here. And actually that's the only input we need. Then let's do an open and closed curly brackets, and inside these curly brackets we're going to write the actual code that is run whenever this function is used. The first thing we need to do inside here is make a new mesh. So I just made an empty mesh, I called it mesh, and then I need to write equals new mesh. This is what's called a constructor. All this is doing, this part on the right is making an empty mesh, and then it's being put into this variable called mesh. So now later in the code we can use this variable called mesh to update and build the mesh. It's all going to be contained in that variable. The next thing we're going to do is make a for loop. For int I equals 0, I is less than input points. Don't worry, I'm going to explain this in a minute. Dot count I plus plus. So what a for loop does is, this is a way to iterate through along a lot of things, and so this is used all the time in coding and writing code and programming. You need to do something over and over and over again, basically the same thing, and so this is something that will do whatever you write inside these curly brackets. It'll do it over and over and over again until you've reached the number of times you want to do it. And in our case, we want to do it, I wrote this wrong, this is supposed to be branch count. In our case, we want to do it for however many branches there are. So I was treating this like a list, but this is a data tree and it has branches. So input lists has, for us right now anyway, it has 151 branches. So you can pretend that this just says 151, so I is less than 151. I starts at 0, so first we're going to do whatever's inside these curly brackets, assuming that I is equal to 0. Then we'll do it assuming I is equal to 1, I is equal to 2, all the way up until we get to 150. Not 151 because when I is equal to 151, it's not less than 151. Anyway, I might be taking too long explaining all this. The next thing we can do when we're in here is make a list. This is how you make a list. You say list, and then you say what do you want to be in that list. In our case, we want it to be point 3D, and then current branch, then you can name it whatever you want, equals input points, and I just realized another mistake I made, dot branch I. So this is going to take the first branch in our input lists data tree and turn it into a list called current branch. And we don't want to go to 151 even. We want to just go to we want to be less than 150. And so our last number here is going to be 149. And that's because for every iteration of this loop, we're going to take 2 points from the current branch and 2 points from the next branch in the tree and use those 4 points together to make one mesh face. So I'm going to copy this again, and let's get the next branch. So we're going to make another list. This one's called next branch, and this is going to be I plus 1. So inputs list dot branch I plus 1. Then we can quickly check to make sure that the same number of points are in both branches. So we'll say if current branch dot count, that's giving us how many points are in that branch, is not equal to next branch dot count. Then continue. Hopefully this will never happen, but we're just going to skip that branch if that happens. And then we'll probably see a hole in our mesh or something like that. Next we can actually make a mesh face. So each iteration of this next for loop, we're going to make a for loop inside this for loop is going to make one mesh face. So we're going to say for int j equals 0, j is less than current branch.count. We're going to iterate through all the points except for the last one, just like for the same reason that we didn't go to the last branch, we're not going to the last point. We don't need to touch those last points. When we get to the second last, those last two will be included. And then j++, then curly brackets, and then we need to grab 4 points for our quad mesh. Each mesh is going to have 4 vertices. So let's say var, or let's say point 3d point 1 is equal to current branch j. And the next point is going to be j plus 1. Then we need 2 more points. So I'm going to copy this twice more. And just because, I'll explain this in a second. Okay, so this is going to be point 2, and then point 3, and then point 4. And this is going to be not current branch, but next branch. So when we're on the first branch, we need whatever j value we're on, and then whatever is the next point in the list. So we'll draw a line from the point that we're on to the next point in the list, then we'll jump up to the next branch, and for j plus 1 again, so the same number here is right here, and then we'll go back to j. And so that's going to make a square, or a rectangle, a quad face. And then we'll say int v1, vertex 1, is going to be mesh.vertices.add point 1. So up here we only had points. We just pulled out the points and gave them names. Here we're actually adding them to our mesh that we made up here. We have an empty mesh up here, and this little line here just says add point 1 as a vertex in our mesh. And what it's returning on the left side of the equal sign is an integer, and that integer is whatever index that mesh vertex is inside the mesh. And I'm sorry, this is getting a little confusing if you don't know C#. If you do, you're probably wanting me to move much quicker, so I apologize in both cases. Anyway, we need 4 integers that are the index numbers for the vertices that we're adding. First we're adding point 1, then point 2, then point 3, and then point 4. And now we have these integers. The mesh stores all its vertices in a vertex list. These are the integers for those vertices. And we need those integers because we want to make a face out of these 4 vertexes, out of these 4 vertices. That's our next step. We say mesh.faces.addFace. And then we just write v1, v2, v3, and v4. And that'll give us a mesh. There's one more step before we return it, and that's mesh.vertices.combineIdentical, and then true, not tour. So this is, when we're going through and doing this, we'll be adding a lot of points multiple times, and so we'll have way too many vertices, or way more than we need. And so this step isn't absolutely necessary, but if you want to get rid of all the extra vertices, you can do that. And then after this, we say return mesh. And so what this says is after you run all of this code, return mesh as the kind of like the product of this function is what it's just made. And so up here, we can say A equals create mesh from tree. So this is just a mesh. When we called the function, it's just returning a mesh. So everything that's in blue up here is just a mesh. That's going in here. We don't need to say what kind of input. It knows that it's expecting a data tree of points. And we wrote A because when I click OK, this is the output. And so we're just telling it to send it out of this output. So now we can hide this. And now we have a mesh that's approximating what the surface of this pasta would look like. And that's it for this video. In the next video, we're just going to play with the variables a little bit to better understand these equations and to better understand how the variables affect the morphology of this pasta. So, hope to see you there.